Okay, so just to pick up where we stopped in our previous lecture, for chapter 2, we keep repeating this equation, which is the non-deforming control volume theorem, which is d dt over rho d volume equal to what happened in the control volume and what happened to the control surfaces, right? So basically this equation is talk about the m dot mass flow rate, and when we need to solve the question, we will assume that continuity equation apply to our volume. So when we apply the continuity, means that there's no losses in our mass. For fixed and non-deforming control volumes, because later on we will learn about deforming control volume. So for fixed and non-deforming control volume, our equation will be equal to 0. So the control volume plus control surfaces will equal to 0. Okay. Then we will go through a few examples already, and we will continue with new things today. Yeah. Okay. Now, for the equation just now, continuity equation that we learned so far is the example that we have so far is having section A and section B, or your inlet and outlet. Previous example is having same area. Okay, but starting from today, we will look at different the changes of your area, and then what will happen to the our continuity equation. Okay. Okay, so I think you're familiar with the equation that you see on the screen here. We are having a control volume dimension and also a control surfaces dimension. Okay, we have two scenarios here. What happens if the flow is steady? Okay, so when the flow is steady, straight away you can draw an arrow and then write steady, then you write equals 0, then you will score some marks for the steady flow scenario. Sometimes the control surfaces will also equal to 0 when we have a steady flow that go across the surfaces, all right? So this component, we will equal to 0. However, to calculate this one, to calculate the control surfaces component, we will calculate what is the mass that going in will equal to going out, that what we already covered in a previous example. So this is the sum of mass going in will equal to mass of going out will equal to going in, right? So the beginning, the first equation, when you derive from continuity equation, you write sum of m dot out minus sum of m dot in equals 0. Okay, now what happens if you have a flow, you have a steady flow, however you plus one more word in the question, or you assume that the flow is incompressible, then you can take out the rho, then the m dot will become q, because m dot equal to rho AV. Okay, just a note now. M dot will equal to rho AV. Okay, so again, without the hyphen, it means velocity. Okay, when the volume represent with this symbol. Okay, this is velocity. So be careful when you write your answer in your answer sheet, yeah, because in this module we will see a lot of time on the volume and velocity. Okay, so be careful in using the capital V. All right. So okay, just now I write rho AV, right? So when when it's compressible, then rho will be the same. So you only left out with AV, area times velocity for the Q, right? Your in will go your same with the out, or you can say that out was same as the in, right? So this is when you have a velocity, steady flow, Then if the question you cannot find any incompressible word, then you use this equation. If the question mentioned that assume that the flow is incompressible, then you can straight away write a rho equal constant or same. Then you can cancel the rho at both ends. Okay. Okay. All right. So another wording that you will see is uniform. Uniformly. When you're having a uniformly, you will also use m dot equal to rho AV, meaning that you also use rho AV in your calculation. However, when you are seeing the velocity is non-uniformly distributed, then we will use v hat. Okay, so if it's uniform, we use the normal velocity. If it mentioned that the velocity is non-uniform, we will convert the non-uniform that we demonstrate in the previous example, the parabolic flow. We convert it to uniform flow in our previous example. Okay, so this is non-uniform flow in the parabolic. So there's an equation for this one. So there's a V here. So when you convert into uniform flow, you use an average velocity. Okay, when it's non-uniform, we will use an average velocity. Okay, and we already go through when we have a parabolic shape of non-uniform, we can write V hat equal to U max. Sorry for my writing. U max divided by 2. Okay, if you're not sure what I'm talking about, go to the previous tutorial slide. Go to the previous lecture video, go and review. Go and listen it one more time. How do we prove from a parabolic shape, only parabolic shape, only parabolic shape will be equal to U max divided by 2. Okay, so this slide is just to show you what happened. You have a non-uniform condition compared to the uniform condition. This is quite straightforward. Okay, let me check the attendance. Okay, Ku and Raj is here. All right. Good. Okay, let's continue. Just now, what we mentioned is that steady and incompressible, what happened to your equation? And then we mentioned what happened when you have a uniform flow and non-uniform flow, what will happen in your, what we expected in your answer. So always check your answer whether you use the correct mathematic presentation. Okay, so when you write something, it means something else. So don't simply give me an equation and then you assume I understand. Okay, I will give you mark based on what we covered in the lecture. Right. Then okay, so this one, when you seeing the V m dot equal to rho AV and the V is with a hat, it means you are using average velocity, meaning that there is a possible that the flow is non-uniform. So when you are seeing the average flow, the wording average flow in the question, it means that you might be having a non-uniform flow. Okay. So these are the mathematic presentation when you have steady flow, one stream. One stream means in one direction. So you're having you can write m dot equal to what is in. Usually we represent section 1 as your inlet, 2 is your outlet. So in will equal to your outlet. But this one is because we are using the average velocity here. So it just means that you take Okay, so it means that you are using the average velocity value. Okay, yeah. Again, V hat is the average velocity. There might be a scenario where you convert parabolic flow V equal change to uniform flow scenario. Okay, like that. Okay, so this is basically the expectation from us in your answer. So far, we're still dealing with m dot. What is the equation for m dot? Rho AV. We keep repeating this equation. I think throughout we will use this equation throughout this semester. All right. Now again, what happens if you see the incompressible flow? Then you can cancel out the for incompressible flow. Remember to write this one to score you some marks. Maybe minimum you'll get 1 mark when you write. For incompressible flow, you write rho equal to constant or rho equals same, or you write rho equal to rho 1 equal to rho 2. Then you can cancel in the formula above. Then you rewrite the equation. You get Q equal to AV. Okay, inlet equal to outlet. So basically, we're still dealing with m dot, where we've seen this one before. Okay. Okay. Though we have done with fixed and non-deforming already. Today we look at moving, non-deforming. Okay. The word is moving. We look at moving control volume, but the control volume doesn't deform, but it's moving. Previous example, we look at fixed, means that the control volume is not moving. All right. Now again, recall that always draw something on your question in your answer sheet. Remember to draw this dot control volume. Then you draw an arrow to show that you understand the steps in analyzing the problems. So always draft the scenario, then you draw the dashed line according to the shape given. You draw an arrow, you write control volume, you'll get 1 mark for the effort to show that you understand how to solve a control volume problem. Okay, now we look at moving control volume. Okay, the word is moving. What type of scenario that we deal with moving control volume? For example, the aircraft jet engine. So the aircraft jet engine, the flow is coming from the left and then eject to the right hand side. Okay, from the front. Then after some processes, it will change. Okay, so this is one of the example where your control volume is changing, not changing. Your control volume is moving. Okay, so as you can see, this is your control volume. Okay, so the air is coming in, and then you're seeing that there are some air being rotated here. Here also rotated. Here also rotated. Okay. And another thing is a ship that go across the sea. So you're seeing that the control volume is changing. Okay, what does it mean? It means imagine this is your control volume. However, the ship, apologize for my drawing, but try to understand, right? So the CV, the control volume is changing as the boat is moving. Okay, now same with this one, this diagram, maybe it seems that the control volume doesn't move. You imagine as an aircraft. Again, apologize for my drawing. Okay, so this is your engine. Okay, so this is your engine. So the aircraft will move through a control volume. The control volume is moving. Okay, so same with the ship also. All right, so today we look at moving control volume. Okay, moving control volume. All right, now before we try to solve a moving control volume, there are new terms that you need to learn today. You need to recognize a vector diagram like what you see on your screen on the left hand side here. Okay, you are seeing three vector here: V, W, and V sub CV. Okay, recognize and memorize the shape. It will help you to solve moving control volume. And the control volume is non-deforming. Moving control volume. Recognize this vector form. Okay, and when you draw this one, if this question asks you to solve a moving control volume, you draw this shape. You draw W, you draw V, you draw CV, you get 1 mark for vector diagram. Okay, now we move forward a little bit. What are all these V, W, and CV? We will need to change our continuity equation, our velocity, to relative velocity. Okay, today you learn a new word. The new word is relative velocity, represented by W. Okay, by this one. This is your relative velocity, W. Previously, we are using this one, and our control volume doesn't move. However, start from today, we are learning about moving control volume. So your control volume is moving. So there's a vector for your control volume. So the differences between your object velocity or your fluid velocity to your control volume. Okay, now just recall that we are analyzing our control volume and our fluid that going in and out into the control volume. So we have our fluid here. Okay, we have our fluid here. I just draw as a small circle just to represent the fluid. But of course, it will, like water, it will just fill the control volume. Right. So since we are studying about the moving control volume, so your vector for your control volume velocity will change a little bit. Okay. Now, what happens if you have a fixed control volume, meaning that everything will be the same? If you have a fixed, the previous one, your V will same, your VCV will same, your W will be the same. Okay, in the same direction. However, for moving, then this straight line will become a triangular form. Okay, try to digest. Today, we introduce you one new technical word. It's called relative velocity, which is W. All right, and this W, how you memorize it? You memorize it as what you observe from far. Okay, what you observe from far. What is the changes between the fluid and the control volume? Okay, you observe what is happening to the fluid, what is happening to the control volume, then you compare the differences. Okay. Another one, V sub CV just means the control volume velocity, like what I explained just now. And this one is seen from a fixed coordinate system. So it means that you just look from the reference coordinate. Normally in the question, you will see X and Y axis in the question. So you're referring this one, V sub CV, from the axis, reference axis in the system. Okay, so if you're having a pipe, for example, normally the x-axis is in the center. Okay, normally the axis will put inside the pipe here. And just to recap, when you deal with pipe, when you have a non-uniform flow, you have a maximum velocity at the center, U max at the center. And you need to consider friction flow. Then at the screen, at the wall there, velocity equals 0. Okay, this one you need to refer if you don't understand what I'm talking about. Why this one is 0, why this one U max, refer back to the previous derivation for pipe velocity. The next one will be absolute velocity, which is your previous, you're using all the while, you're using the absolute velocity, which is the fluid velocity. Okay, this one is in the keyword is the you are from a non-moving observer. Okay, but anyway, 3 new things that you learned today. Most important one is relative velocity, which is W. It's the differences between or the changes of your fluid to your control volume. Okay, so you just try to understand what is happening here. Is that your control volume and your fluid is changing. Okay, your fluid is changing. Fluid can be gas, can be water, can be mercury, can be anything. So far we are not dealing with gas. So far we're not dealing with gas yet. We're not dealing with gas yet. Because yes, gas can be compressed. So when it compressed, a roll is happening and thermodynamics will coming in. So far we're dealing with fluid with control volume. Okay, memorize this shape is important to solve. Okay, then once you draw this one, once you draw the shape, you know that vector, you can relate them with the vector equation. So if you are drawing a vector, for example, vector A, continue with vector B. Let's say you have 2 vectors. The resultant from here, from A, will give you C. So vector C will be equal A plus B. This one fall under vector chapter. Again, if you don't understand the principle of adding and subtraction of vector, open up your advanced calculus or your advanced mathematics. There's a chapter on vector. So try to understand how you draw vector and how you calculate vector. All right. So what happens if you have a dot products vector, when you have a cross product vector, what happening to the operation? Okay. So this is the fundamental for vector. When you draw this kind of diagram, it means that this is your starting. This is not starting. This is your first vector, second vector. This is your resultant. Okay, resultant always on the left hand side. Your other vector will on the right hand side. Okay, so this is quite straightforward so far. There is no complicated, only the new terms that we learned today. The V, CV, and W. Again, W is a relative velocity. So this also another bonus mark. If you write this equation, if you draw this one, you get 1 mark. You write this equation, you get 1 mark. Okay, so it will help you score some marks here. Then what is the changes when you deal with moving control volume? What will happen to your continuity equation? If you study the equation that on your screen here, the left hand side, the system will be the same. The control volume will be the same. only the V velocity for the control surfaces is changing. It will become W when you are solving moving control volume. The previous one, fixed one, we use V. But for moving, we use capital W. So take note. Take note. So this is very important because when it comes to tests, you need to look at the question whether you are solving moving or fixed control volume scenario. So if you write V for the moving control volume, straight away you lost the whole questionnaire. Okay, because you are using the wrong equation to solve. Okay, I will not do the correction for you in the exam. I will look for the correct answer or correct equation. I will not assume this one equal to that one. I will just look at what you write on your answer sheet. I will compare to the standard answer, and you do not give me the expected answer, I will give you wrong. So be careful on what you write in your answer. Okay, so again, for moving control volume, remember to change to capital W. All right. So a few new things for today. The vector diagram, and then the vector equation. And remember to change the form of your continuity equation. Or I cannot use the continuity because this is your conservation of mass equation. Because when you mention the continuity equation, there will be 0 inside these two. Okay, these two will equal 0. Then it means continuity equation. Okay, so this whole thing means conservation of mass equation. Okay, conservation of mass equation. All right, and you see when you write capital W again, it is meaning that we are looking at moving control volume. Okay. All right. So same. If you talk about continuity equation, remember when you look at moving control volume, change the V to capital W equals 0. Then we are knowing that you are solving a moving control volume scenario. Okay. Any questions so far for the general equation or anything that I'm not sure what is capital W, what is the vector meaning and all this? Okay. Any question? Now we look at application of the theory that we learned so far, how we apply for the moving non-deforming volume. Then we will go for a short break. Okay, then we continue for the rest of the lecture. Okay, now this equation, this example is available in your tutorial question. Okay, so let's look at the tutorial question. As you can see, the question say that the aircraft is moving forward. There's a direction there, moving forward at a speed of 971 kilometer. There's a speed given, and the frontal intake area of the jet engine is something 0.8 meters square. So this is the engine that the question will focus on. So it means that this one will give you an area of 0.8 here. There's an area over here. So the area is given. Okay, velocity is given. So just a quick question. Okay, what happened to Raj? Okay, cool. Are you there, cool? Just a quick question.
Yes, sir.
Hold on, let me text Raj a bit. I need to know what happened to Raj. Okay, cool. What is the parameter that you have when you take velocity times area, what do you get? What is the parameter that we are looking at? Okay, I'm back to the screen here. You have given the area of the engine here. You are given the velocity. So when you take velocity times area, what parameter you get? What is the product that we call? What is the name for the product of V times A? Could you understand what I'm asking?
Yes.
So what is the product? V times A. Dennis, I'm going to ask you if Ku not able to answer.
Meter cube, right?
Meter cube over?
Meter cube over S.
S is what?
Second.
Okay, meter cube over second, what is that? What is the name for the products? Let's say you try to communicate with other engineer. What is the name for this one?
Mass.
You get meter cube over second. What is the name for? This is unit. This is called unit. But what is the products when you take velocity times area? Well, what is the name for the products between these two? Dinesh, are you there? Dinesh?
Yes, sir.
Okay, what is the products that we call when you take velocity times area?
Is there density?
Now, what is the name that we call for this
Scalar
product?
quantity.
What is the
Density, right?
You get the unit. The unit is meter cube over second. Cool, you correct for the unit already. I just want to ask, what is the name for these products? For example, you ask question or you say something about the products of velocity times area. You don't tell people something meter cube over second, right? You tell something about what? What's the name of these products? Raj, are you there, Raj?
Vector, sir.
Raj, are you there?
Yes, sir.
Okay, Raj, what is the products that we call when we take velocity times area? Maybe Shirley, you stand by the answer. What does we call when you take velocity times area? What is the products that we call? Let's say the question asks something about the products. The question, how will the question ask you? What is... Okay, apologize.
Volume flow rate.
Correct, volume flow rate. We use what symbol for volume flow rate? The answer is volume flow rate, but what is the normal symbol we use for volume flow rate?
Q, sir.
Q, correct. Raj, right? Raj is the one answer, right?
Yes, sir.
Okay, good, excellent. Dinesh and Ku, I will keep asking you this kind of question, all right, until you subconscious you also know how to answer. All right. the dot products between the area and velocity is given, so you can calculate the Q already. Yeah? You can calculate the Q. So there are some marks that you can pick up from here when you calculate the Q. All right, so we continue with the question. Area is given, entering air density is given, So you have rho, you have the rho, you have the area, you have the V. Basically, you can solve using the conservation of mass equation. And to solve a moving control surface, usually we will consider continuity equation, which is equal 0. Okay. Or in equal to mass out. Okay. So this is the concept before you solve. Don't panic when you solve a very lengthy question like this. You try to accept what information you have, and then try to link with the principle that we learn here. Okay, so far we still at the equation, the conservation of mass equation. Only this is the example for moving control surfaces, control volume. So we're just changing one of the U to W. So a stationary observer determined that relative to the Earth, the jet engine absorbs gas away from the engine with the speed of this one. So you have the word relative. Try to learn what we covered so far. I think 10 minutes ago I mentioned something about relative. So link this relative to this number. Okay, relative you always link with your W. Okay, yeah. So the engine exhaust area again given. So you have another area here at the back of the engine. Means exhaust. Exhaust means your output. Area is given here. So you basically you have all the information. And the exhaust density also given. So they have two density there in the question. One is your input, one is your output. So for this module, when I write rho 1 means input, rho 2 means output. Usually lah, okay, usually. Because we always have your input at station 1, output at station 2. So this is why I'm meaning when I write rho 1 means your input, rho 2 means your output. We need to estimate the mass flow rate, which is m dot, the fuel into the engine, in the unit of kilogram per hour. Kilogram per hour. Because in airlines, when you talk to pilot, when you talk to Petronas fuel tanker, or you communicate with your company that you need to do refueling, then this is the unit that usually we key in your logbook, right? In your technical logbook. Okay. So I'll highlight all the technical word that I mentioned just now. So the next step is what you see on the screen here. The first steps will be, I will just break the diagram into a few steps. The first one, you sketch the solid line, which is the engine. Step 1. Sorry. Okay, step 1, you draw the engine shape. And you will have a fuel going in. And there's an air coming in and going out. Okay, you draw the solid line, which is your system, with your fuel going in, a wind coming from the left into right. So you label stage section 1, section 2. Okay. Step number 2, draw your control volume with red dot or dash line. Okay. Then step 3, label your inlet, outlet. Then you fill in all the information given in the question. So the plane direction, V. This is the information. Step number 5, just fill in the information. Just look at the diagram. You know that we learned something new today. The velocity of the plane is moving forward, and the velocity, you have two kinds of velocity here. Velocity plane moving forward. You have an exort velocity v2 here, item number 6, and then you need to add one more component in your diagram, which is the relative velocity. Okay, relative velocity also given. So relative velocity for your inlet will same as your plane movement. Okay, the same as your plane movement, but the direction will be different. Okay, velocity will be sucked into the engine. The fluid is going in. Again, this W will deal with fluid, not the plane. So V plane moving forward to the left. However, for the fluid, for the air, is going into the engine. So change the V or the previous capital V into W in this example. Okay, yeah. So this arrow is deal with fluid. This one also deal with fluid, or your gas, or your air. Okay. So the fluid at the exhaust there is addition to the inlet here. So V2, by logic, it will be faster compared to the previous one because W is relative. Okay, relative. Okay, the word relative means you stand from a point, then you observe what happened to the fluid. You will see that the fluid is moving faster after it's eject from section 2. The output will move faster. So your W2 will be plus 971. Okay. So this is the steps before we start solving. Make sure you know how to draw the diagram before you solve the mathematics area. Okay, so draw the solid line. There's a where is the input output? So this is the jet engine. So the fuel will going in somewhere. So you need to add in there. So normally the question will give you the solid line diagram. Then you need to draw the red color or maroon color control volume. Then you add in the W. Normally won't be draw for you, right? The velocity also won't be given, so you need to add in the arrow yourself in the diagram. Okay, label section 1 or inlet, label section 2 as outlet, then you get some marks for, maybe 2 to 3 marks for your diagram. For sure, when you draw the control volume, sure you get 1 mark for your control volume. Okay, we move to the next slides. Just to recall that we learned a new vector diagram today, V, VCV, and W. Okay, so back to the question. I put the diagram on the right hand side of your screen. We need to estimate the mass flow rate that go into the engine. So first step, after you draw the diagram, you call the conservation of mass equation, which is this one. Again, we are looking at moving control volume. Something changes in our equation. If you write V, I'll give you wrong answer. Okay, so if you are having a moving scenario, then you need to change the W in the equation or in your answer. Now, how do we know that you need to use W in your equation or in your answer? You read through the question. they will be relative word used inside the question. When there is a relative wording inside the question, it means you need to use relative velocity, which is the W must appear in your answer. Okay, these are all the keywords that will help you to solve. So when you write the equation, this one will give you 1 mark for the application of continuity equation. Then the next question, this just help you to solve a little bit. Is you need to think about the flow relative to the moving control volume. Okay, so we have a steady flow. Okay, we will have a steady flow that go into the engine. So the next steps is that you draw an arrow for the to cancel the control volume dimension. Then you write steady equals 0. Then you get another point for the steady flow scenario application. Okay. Now, although there is no uniform flow, there is no steady flow here, we will use this approach. However, in exam, you will see steady flow inside the question. Okay, it will help you to score some marks. So when you look at the question will always I'll give you some marks there. So you need to be smart enough to see the keyword that I give you to solve. All right. So you will see steady flow inside the question, especially when it comes to exam or test. Then you can draw the green arrow with 0 and steady. You score marks for that, and you only need to solve for this component. So the rest will be the same as what you learned previously, only today we look at W, which is relative velocity. I think I don't need to explain why there is a negative, why is a positive there. Okay, so we need to recall there's a section that I purposely explained about the negative sign. So the field on the top corner here. So y is negative. You draw the surfaces. The field is going in. This is your field. The area will always pointing outward to the opening, right? Always pointing outward. A. Pay attention. This one is also one of the popular area where students will fall into mistakes. They don't know whether it's positive or negative. Okay. So draw the surfaces of the opening. Look at the float itself. For the first one is field going in. So you draw the flow is going into the surface. And the surface area will always pointing to the opening. Or pointing out, always pointing out. Okay. So you look at the arrow direction. If it's opposite direction, then you get negative sign. Then look at here, inlet, you draw an inlet. Okay, you sketch by the side of your answer. You write inlet there. So the velocity is going in. All right, velocity is going in because we are looking at don't confuse with the V plane. We are focusing on W here, which is the relative velocity. W fluid, your fluid or your air is going into the surface, and outlet area will always pointing out to its opening. So area here is pointing out. So you look at the arrow, opposite direction, you get negative sign. So same with the outlet or exhaust. Relative velocity eject out, W. Area always pointing to the opening, to the space here, area. So same arrow, dot product, same arrow will give you positive sign. Okay, the rest is just a substitution of all the value inside here. Okay, make sure you understand how to develop equation from control surfaces. This one, the second equation on the screen, to here. Basically, you just memorize. Try to look at the opening that you have. So we have 3 opening here, and then recall the velocity. If it's fixed, then you use V. If it's moving, then you use W. So in this case, we use W. Then opening always pointing out. You look at these 2 arrows. If they are pointing same direction, then you get positive sign. Stop me if you're not able to understand what I'm talking about. Yeah. Then, because we are interested in finding the field component, so we just rewrite the equation. You put the m dot field in on the left hand side, then you move other parameter to the right hand side. You will get m dot field in equal to rho a w, not v. Be careful. In your answer, if you write V, I will give you a wrong answer. Then I will see your calculation whether correct or not. Okay, you have no point for your equation if you write V in your answer for a moving control volume. For moving control volume, the keyword is relative. So relative velocity, we are using W in our lecture. Okay. So after you rearrange the equation, the rest is just substitution. Okay. So the rest come to here. Then the next one is to draw the vector diagram. So recall the vector equation. V equal to W plus V, your control volume, right? So V2 will equal to W plus V plane. We are interested to find what is our W. So you rearrange the vector equation to W2 equal V2 minus V plane. So V2 is given in the question. V2 is 1050. Your plane here is 971. Okay, your vehicle, your aircraft is moving in 971. So what I need you to pay attention to is that from here, this is the vector equation. When you rearrange, you get a negative sign. So follow to carry forward the negative sign. Only when you substitute, you need to look at the arrow of your velocity. In this case, your plane velocity is to the left. Okay, this is your V plane. That's why we have a negative sign there, because by default, all the direction to the right is positive. So be careful. This also one of the critical area where students make mistakes. They will forget the direction of the vehicle. So this also one of the area where students lose mark and they make mistake in the final answer. Take note on this one. Okay. So negative, negative, we get positive. W2 will be higher number than the previous one. That's why you get a positive sign here. Okay, W2, you get one number. You substitute, you will get m dot fill in equal to 9,100 kilogram per hour. Okay. All right. Now, why we can straight away use kilogram per hour, because the question asks us to solve in kilogram per hour, and all the unit that given in the diagram or in the question is in the unit of kilogram per hour. So you don't need to convert unless the question asks you to find kilogram per second or per minute or something. Okay. Okay, let me stop the recording.